basically you're dominated by proteobacteria. And what's also very interesting is that these proteobacteria are alpha proteobacteria. These are the ones you see that are the dominant members in the ocean. Not only that, the dominant player in this group of alpha proteobacteria is an anoxygenic phototroph. Let that kind of absorb. As well as these firmicutes, these things look like bacillus, so they're heterotrophic, and then cyanobacteria. But you see basically a complete change between both the water column as a function of depth in the microbialite, and it's completely different. Now, going back into metabolism, so I can reconstruct the metabolism of these guys. And I'm just going to show a brief plot of that. But you can kind of do peg mapping, and you can really reconstruct the pathways that you find in the microbial. And most of them hit nothing. Basically, you have nothing. You have nothing. We don't even know what they are. The main one that's kind of hit to me was this idea of carbohydrates. So you have things that are basically degrading the microbial mats that are then taken up by the microbes and then going on from there. As well as you have nitrogen metabolism and sulfur metabolism, which is more prevalent than the oxygenic photosynthesis. So back to this, it's ruined again. But basically, this is not the whole story. It's much more complex. You have, like I said, this dominant member doing oxygenic and oxygenic photosynthesis, making the microbialites, and you have these heterotrophs which are degrading this carbon. But you also have all these other chemistries in sulfate and nitrate that actually form the rocks. So to kind of summarize this up, it's a very complex community full of proteobacteria, who's the dominant members, mainly proteobacteria, the alpha proteobacteria. Is oxygenic photosynthesis the only metabolism present? Absolutely not. You have sulfate reduction, nitrogen, and the degradation of the mats leading to the formation, not just anoxygenic photosynthesis. So basically, the cyanos are the microbial salad bar that are giving rise to the formation of these structures. So, got anything out of this today? 85% of the Earth's history has been dominated by these structures. They are globally abundant and still active. They are intensely complex communities, and metabolism is also very complex, and that the cyanos are critical in maintaining this microbial salad bar. So I wanted to thank various members of my lab, especially Marley Luke, the lone botanist, and Curtis Suttle, and various others. And thank you very much for your time.
Do we have time for questions?
That was really interesting. So I was fascinated by your first, one of your first graphs that showed that microbialites have been around for 3.5 billion years, but stromatolites have only been around for about 2.8, right?
So the oldest stromatolites are 3.5, and they just had a paper in Nature talking about the use of sulfate reduction in these ancient West Australian stromatolites.
Okay. So I guess my question was really, are there a lot of these structures that either don't contain cyanobacteria, or if you looked into a modern day stromatolite, do you find a lot of these other bacterial, non-photosynthetic processes happening? So my assumption was always that they were cyanobacteria dominated like everybody else.
This has been the kind of the dogma, and there's been 2 papers in Nature, I can definitely send you those, that have talked about there's no evidence of the ancient stromatolites being formed by cyanobacteria. So I'm looking for, trust me, I want to find an anoxic environment where these structures are being made, and you have a different guy doing the work. My best guess is that there is no evidence of this, all right? Either we got to change that date or find a better way to extract nucleic acids at that time, or it's something else. It's something like a green non-sulfur. So green non-sulfur, it makes lots of filaments. It's something like chloroplexus. It could be making these ancient mats, and some of the dendritic structures that we see could definitely be pointing to that. But I would love to find an anoxic stromatolite or microbialite with no cyanobacteria present. And I think that is what will change the game. Or we find one that or it is what it is, and we can't tell. But it's a great question. It's a great argument in science about these 2 processes. Thank you. Good question. So we also have Kelly Lake, which is literally, I think, about 20 minutes away, and we see something very similar. And maybe they're fed on the same water column. I don't know. The ones in Lake Van, which are hypersaline, they're giant. They're as big as cars. They're as big as this table, right? And they have similar cone-like structures. We find the cones more present. So we find in the hot frying pan lake in New Zealand, which is at 90 degrees, you have these giant cone structures. As well as in Yellowstone, there are silica-based microbialites, which is something I didn't talk about today, and other conal cyanobacterial stromatolites. But as far as the diversity as a function of depth, I think it's a BC thing. But I'd love to see other places. And I've been looking all over. So.
Right, let's thank Rich.